For decades, the concept of quantum computing has hovered like a tantalizing dream. Imagine computers not just faster, but fundamentally different, capable of tackling problems that would take today's most powerful supercomputers billions of years. We're talking about designing life-saving drugs molecule by molecule, creating uncrackable encryption and breaking current codes, revolutionizing financial modeling, and developing artificial intelligence far beyond our current comprehension. How? It all comes down to the qubit. Unlike the simple 0 or 1 of classical bits, a qubit, thanks to the bizarre rules of quantum mechanics like superposition, can be a 0, a 1, or both simultaneously. And through another spooky phenomenon called entanglement, qubits can be linked, their fates intertwined no matter the distance. This exponential power is staggering. 2 qubits can represent 4 states at once, 3 can represent 8, and 300 qubits could represent more states than there are atoms in the known universe. Sounds incredible, right? But here's the massive roadblock, the elephant in the quantum room: errors. Qubits are the divas of the computing world. They are incredibly fragile. The slightest vibration, a stray magnetic field, even a tiny temperature fluctuation. Basically, any interaction with the outside environment can cause their delicate quantum state to collapse, introducing noise and errors into the calculation. This phenomenon, called decoherence, is the bane of quantum physicists. Imagine trying to perform a complex symphony on instruments that go wildly out of tune if someone even breathes near them. That's the challenge. For years, scientists have wrestled with quantum error correction. Traditional methods often involve using many physical qubits to represent a single, more stable, logical qubit. You run calculations multiple times, compare the results, and try to statistically filter out the errors. Think of it like taking multiple blurry photos of something and trying to digitally combine them to get a clearer image. It can work, but it's painfully slow, requires an enormous overhead of extra qubits, sometimes thousands or even millions of physical qubits for one logical qubit, and consumes vast computational resources just for the correction process itself. This makes scaling up quantum computers for practical, real-world applications seem almost impossible. It's like needing an entire football field filled with musicians just to reliably play a single, perfect note. How can we ever build a full orchestra this way? This is where Nvidia's strategy becomes so fascinating and potentially game-changing. They looked at this monumental challenge, the qubit instability, the cumbersome error correction, and said, hold on. We're not experts in building the delicate quantum cores, the qubits themselves, but we are world leaders in AI and high-performance supercomputing. What if we use our strengths to solve their biggest weakness? Nvidia isn't trying to build the quantum violin. They're building the ultimate conductor, tuner, and acoustic engineer, all rolled into one, powered by AI. Their newly announced NVIDIA Accelerated Quantum Research Center, NVAQC, is the crucible for this vision. The core idea is deceptively simple yet profound. Use AI to predict and correct quantum errors in real time, orchestrated by classical supercomputers. Think about it. Machine learning algorithms excel at recognizing subtle patterns in vast amounts of data. Nvidia is training AI models to constantly monitor the state of the qubits, learn their error patterns, how they tend to drift, wobble, or decohere under different conditions, and predict errors before they even fully derail the computation. Imagine an AI that knows, okay, based on the current environmental noise and the operations being performed, qubit 17 is likely to flip its phase in the next microsecond. These AI-driven predictions and correction instructions are then fed instantaneously to powerful classical supercomputers. The kind Nvidia is famous for building, think their DGX systems. These supercomputers process the corrections and adjust the control signals going to the quantum processor on the fly, stabilizing the qubits, and keeping the quantum calculation on track. It's like having an AI co-pilot constantly making micro-adjustments to keep a hypersonic jet stable. The result: instead of slow, after-the-fact error correction requiring massive qubit overhead, you get real-time stabilization. This could dramatically reduce the number of physical qubits needed for a reliable logical qubit, potentially making quantum computers far more stable, scalable, and ultimately useful. It's a massive potential speed boost, not just in raw calculation, but in making the whole process of quantum computing viable. Nvidia aims to transform quantum computing from a delicate laboratory experiment into a robust, practical tool for large-scale problem-solving. As Tim Costa, Nvidia's Senior Director for Quantum and CUDA-Q, outlined, NVAQC is zeroing in on three critical pillars. 1. Large-scale simulations, using their supercomputers to simulate incredibly complex quantum algorithms and even different quantum hardware designs. This lets them test and refine both software and hardware concepts much faster than building physical prototypes for everything. It's like having a virtual wind tunnel for quantum processors. 2. Seamless hybrid integration. This is key, making quantum processors work hand in glove with classical supercomputers. Most complex real-world problems will likely require both types of processing, quantum for the parts classical computers struggle with, and classical for everything else: data preparation, result analysis, controlling the quantum part. Nvidia wants this integration to be effortless. 3. AI for quantum stability. Developing, training, and deploying those specialized AI models specifically designed to understand quantum noise, predict errors, and enhance the stability and coherence of qubits. This is where their AI expertise directly tackles the core quantum challenge. Nvidia isn't just building another quantum chip. They're building the intelligent scaffolding and control system that might finally allow all quantum chips to reach their potential. If they succeed, this approach could be the catalyst that moves quantum computing out of the realm of theoretical physics and into the hands of scientists, engineers, and businesses solving real-world problems. But Nvidia understands a fundamental truth: the race for quantum supremacy, or perhaps more accurately, quantum utility, is far too complex for any single company to win alone. Building a functional, scalable quantum ecosystem requires expertise spanning physics, computer science, engineering, software development, and domain-specific knowledge in fields like chemistry and finance. Recognizing this, Nvidia has forged powerful alliances, bringing together some of the brightest minds and leading innovators in the quantum space. This isn't just about pooling resources. It's about creating a synergistic environment where different approaches and technologies can converge. Let's look at some of the key players Nvidia is collaborating with through NVAQC. Quantinuum, a heavyweight formed from the merger of Honeywell Quantum Solutions and Cambridge Quantum. They are leaders in traption quantum computing technology, known for achieving high qubit fidelity, meaning their qubits are relatively stable and accurate. They also have deep expertise in quantum software and algorithms. Partnering with Quantinuum gives Nvidia access to top-tier hardware to test and refine their AI-driven error correction and hybrid integration strategies on a leading platform. Imagine Nvidia providing the AI brain and Quantinuum providing a high-performance quantum engine to plug it into. QuEra computing. These folks are pioneers in a fascinating and promising area: neutral atom quantum computing. Instead of using charged ions or superconducting circuits, QuEra uses lasers to trap and manipulate hundreds of individual neutral atoms to act as qubits. This approach holds potential advantages in scalability. It might be easier to pack more neutral atoms closely together, and coherence. Neutral atoms might be less susceptible to certain types of environmental noise. Collaborating with QuEra allows Nvidia to explore and support diverse quantum hardware architectures, ensuring their AI and supercomputing framework is adaptable and not locked into just one type of qubit technology. It's like designing a universal engine control system that can work with gasoline, diesel, or even electric powertrains. Quantum machines. Building a quantum computer isn't just about the qubits. You need an incredibly sophisticated classical control system to orchestrate everything, sending precise microwave or laser pulses to manipulate the qubits, managing the measurements, and coordinating the flow of information. Quantum Machines specializes in exactly this, building the quantum orchestration platform. Their hardware and software act as the crucial intermediary between the classical control computers and the delicate quantum processor. Partnering with them is vital for Nvidia's vision of seamless integration. Nvidia's AI needs a reliable, high-speed channel to influence the qubits, and Quantum Machines provides that critical piece of the puzzle, ensuring the AI's corrections can be implemented effectively in real time. But the collaboration doesn't stop with industry partners. Nvidia is also deeply engaging with academia, tapping into foundational research and the next generation of quantum talent. Harvard's Quantum Initiative brings world-class theoretical and experimental physics expertise, pushing the boundaries of fundamental quantum science. MIT's Engineering Quantum Systems Group focuses on the practical engineering challenges of building robust and scalable quantum technologies. This blend of industry pioneers and academic powerhouses underscores a crucial point. Nvidia's effort isn't just an internal project walled off from the world. It's a deliberate strategy to build an open, collaborative quantum ecosystem. They are positioning themselves not just as a component provider, but as a central enabler, providing the AI and supercomputing infrastructure that other quantum innovators can leverage. Why does this matter so much? Because it dramatically increases the odds of success. By working with diverse partners, Nvidia can test its approach across different qubit modalities, learn faster, and develop solutions that are more broadly applicable. It also signals to the entire industry that Nvidia is serious about making hybrid quantum computing a reality now, not just in some distant future. And crucially, Nvidia already possesses the powerful underlying technology to make this intricate dance between classical and quantum systems happen. Nvidia hasn't just woken up and decided to jump into quantum. They've been laying the groundwork for years, developing the specific hardware and software tools needed to bridge the gap between the classical computing world they dominate and the nascent quantum realm. With the launch of NVAQC, these tools are now taking center stage, forming the technological backbone of their quantum strategy. Two pieces of technology are particularly vital. DGX Quantum. This isn't a quantum computer itself. Instead, think of it as the world's first GPU-accelerated quantum computing system. It's a sophisticated hybrid platform specifically designed to tightly integrate a traditional Nvidia GPU-powered supercomputer, like their powerful DGX A100 systems, with third-party quantum processing units, QPUs. It provides the high-speed, low-latency communication links and the shared memory architecture necessary for the classical and quantum components to work together seamlessly. Imagine a complex problem, like designing a new catalyst for green hydrogen production. Parts of the problem, like simulating the intricate quantum interactions between molecules, are perfect for a QPU. But other parts, like preparing the input data, running classical simulations for comparison, analyzing the quantum results, and crucially, running the AI error correction models, are best handled by powerful classical GPUs. DGX Quantum is the orchestrator, the central hub that allows these different processors to collaborate efficiently on the same problem, passing data back and forth rapidly. Nvidia has already deployed DGX quantum systems in partnership with quantum hardware companies, giving researchers unprecedented access to run these complex hybrid workflows and simulate quantum systems at scales previously unimaginable. It's the physical embodiment of Nvidia's hybrid vision. CUDA-Q, formerly known as QODA Quantum Optimized Device Architecture. If DGX Quantum is the hardware bridge, CUDA-Q is the essential software framework, the common language that allows developers to build and run these hybrid applications. Building on Nvidia's wildly successful CUDA platform for GPU computing, CUDA-Q is an open-source platform designed specifically for hybrid quantum classical computing. It allows programmers to write code that can seamlessly allocate tasks to CPUs, GPUs, and QPUs, all within a single application. Crucially for Nvidia's strategy, CUDA-Q makes it much easier to integrate AI with quantum computing. Developers can use familiar programming models, like Python, and leverage Nvidia's extensive libraries for both AI, like cuDNN, and scientific computing, alongside quantum programming tools. This lowers the barrier to entry significantly. You don't need to be a master of 3 different programming paradigms. CUDA-Q provides a unified environment. This is absolutely critical for developing, testing, and deploying the AI-driven error correction models that are central to NVAQC's mission. It enables researchers to rapidly prototype AI algorithms for quantum stabilization, simulate their effectiveness using GPU acceleration, and eventually deploy them on real hybrid systems featuring DGX Quantum and partner QPUs. These tools aren't just theoretical concepts on a roadmap, they are deployed technologies. Nvidia is already enabling researchers to perform real-world quantum simulations and hybrid computations today. This represents a pivotal shift. For years, quantum computing felt confined to theoretical papers and specialized labs. Nvidia, by providing this practical, scalable, and AI-enhanced hybrid infrastructure, is actively pulling quantum computing out of the lab and paving the way for its integration into mainstream scientific and industrial applications. If this approach works as envisioned, the impact across numerous fields could be staggering, solving problems currently considered intractable even for the mightiest classical supercomputers. So let's assume Nvidia's strategy succeeds. Imagine a world where stable, scalable, AI-enhanced quantum computing becomes accessible. What does that future look like? The potential impact isn't just incremental, it's transformative, promising to redefine entire industries and unlock capabilities we can barely conceive of today. Artificial intelligence reimagined. Right now, training cutting-edge AI models like GPT-4, Claude, or large scientific AI requires colossal data centers packed with GPUs, consuming enormous amounts of energy and time. Quantum computing, particularly when boosted by AI for stability and potentially even developing novel quantum machine learning algorithms, could change the game entirely. Imagine training neural networks exponentially faster. This wouldn't just mean quicker updates to existing models. It could enable the development of vastly more complex and powerful AI architectures that are simply infeasible to train today. We could see breakthroughs in natural language understanding that lead to truly conversational AI, leaps in computer vision for autonomous systems, and AI capable of discovering complex scientific principles from raw data. Quantum AI could accelerate the entire field of machine learning, potentially leading to artificial general intelligence, AGI, sooner than many predict. A new era in medicine and materials. One of the most computationally demanding tasks is accurately simulating the behavior of molecules. Classical computers struggle because the quantum interactions governing molecules are incredibly complex. Quantum computers are naturally suited for this. Combined with AI for error correction and analysis, we could design drugs atom by atom, simulate exactly how a potential drug molecule interacts with proteins in the body, drastically speeding up drug discovery and reducing costly trial-and-error lab work. Imagine personalized drugs designed based on quantum simulations of your specific genetic makeup and biochemistry. Unravel diseases. Simulate the complex process of protein folding, which is implicated in diseases like Alzheimer's and Parkinson's, leading to new diagnostic tools and treatments. Discover new materials. Design materials with specific properties from the ground up, superconductors that work at room temperature, ultra-efficient catalysts for clean energy production, like splitting water for hydrogen fuel, or materials for better carbon capture. The future of security. This is a double-edged sword. A powerful enough quantum computer could theoretically break most of the encryption methods, like RSA, that currently protect everything from online banking to government secrets. This is a serious threat. However, Nvidia's AI-driven quantum approach could also be instrumental in developing and testing new post-quantum cryptography, PQC, algorithms, encryption methods designed to be secure against attacks from both classical and quantum computers. AI could help identify vulnerabilities in proposed PQC standards much faster, ensuring our digital world remains secure in the quantum era. Understanding our planet and climate. Climate modeling involves simulating incredibly complex interactions between the atmosphere, oceans, ice caps, and land surfaces. Even supercomputers struggle with the required scale and detail. Quantum simulations, stabilized by AI, could provide far more accurate and granular climate models. This could lead to better predictions of extreme weather events, more reliable long-term climate change forecasts, and more effective strategies for mitigation and adaptation. Revolutionizing finance. The financial world thrives on data analysis and prediction. Hedge funds and banks already use sophisticated AI for algorithmic trading, risk management, and fraud detection. Quantum algorithms could take this to another level entirely. Imagine optimizing complex portfolios, simultaneously analyzing billions of market variables and potential future scenarios to find optimal investment strategies with unprecedented speed and accuracy. Pricing derivatives, more accurately pricing complex financial derivatives whose value depends on many interacting factors. Enhanced risk modeling, running sophisticated simulations to better understand and mitigate systemic risks in the financial system. Institutions like NASA for optimizing complex missions. Major pharmaceutical companies and financial giants are already exploring quantum applications. What makes Nvidia's approach potentially pivotal is that it doesn't require waiting for perfectly fault-tolerant quantum computers, which might still be decades away. By integrating AI and supercomputing now, they aim to make today's noisy, intermediate-scale quantum (NVAQC) devices, and those of the near future, significantly more useful and practical for tackling parts of these massive challenges. They are building the bridge to the quantum future and allowing us to start crossing it much sooner than expected. While Nvidia's AI-centric hybrid strategy is compelling and unique, they are definitely not playing on an empty field. The quest for quantum advantage is attracting massive investment and brilliant minds from some of the world's largest and most innovative tech companies. Understanding how Nvidia fits into this competitive landscape highlights the significance of their approach. IBM, a true pioneer in the field. IBM has been relentlessly focused on building increasingly powerful and accessible quantum computers for years. They were among the first to put quantum computers on the cloud, IBM Quantum Experience, for researchers and developers to experiment with. Their Quantum System 1, and subsequent iterations represent a push towards making commercial quantum computing a reality, focusing on improving qubit quality, coherence times, and building a robust software stack (Qiskit). IBM's strategy is heavily invested in building the end-to-end quantum system and making it available as a service, aiming for broad enterprise adoption. They are building the quantum engines and inviting people to use them. Google's quantum AI division grabbed headlines in 2019 with their Sycamore processor, claiming to have achieved quantum supremacy, performing a specific, carefully designed task far faster than any classical supercomputer could. While the specifics of the claim were debated, it marked a significant milestone. Since then, Google has focused on improving qubit fidelity, exploring error correction codes, and scaling up their superconducting qubit processors. Their goals seem centered on demonstrating clear quantum advantage on scientifically or commercially relevant problems, pushing the boundaries of what's computationally possible with quantum hardware. They are aiming to build the undisputed fastest quantum race car. Microsoft is playing a longer, perhaps higher-risk, higher-reward game. They are heavily invested in developing topological qubits. These are based on exotic quasi-particles and theoretically could be inherently much more stable and resistant to noise than other qubit types like superconducting circuits or trapped ions. If successful, topological qubits could leapfrog many of the error correction challenges faced by other approaches. However, reliably creating and manipulating these topological qubits has proven extremely difficult, and Microsoft's hardware development is still in earlier stages compared to IBM or Google. In the meantime, their Azure Quantum platform offers cloud access to various third-party quantum hardware, including from Nvidia partners like Quantinuum and Software Tools, positioning them as a versatile cloud provider for the quantum ecosystem, regardless of whose hardware ultimately wins out. They are betting on a revolutionary new engine design, while also building a universal garage, Azure, that can service any type of quantum vehicle. So, where does Nvidia slot in? Their genius lies in not directly competing on building the best standalone QPU, at least not initially. Instead, Nvidia is leveraging its existing dominance in GPUs and AI to become the indispensable enabler and integrator. The hybrid advantage. While IBM, Google, and potentially Microsoft focus on building powerful, purely quantum machines, Nvidia recognizes that most real-world applications in the near to mid-term will likely be hybrid. By mastering the seamless integration of classical supercomputing, GPUs, and quantum processing, QPUs, via DGX Quantum and CUDA-Q, Nvidia provides a practical pathway for businesses and researchers to start harnessing quantum capabilities without abandoning their existing classical infrastructure or waiting for fault-tolerant quantum computers. The AI edge. Nvidia's deep expertise in AI is its unique weapon. Using AI for real-time error correction and stabilization directly addresses the biggest bottleneck holding back all quantum hardware platforms. If successful, Nvidia's AI could make everyone's qubits better and more useful, positioning them as a crucial partner rather than just a competitor. Ecosystem building. Through strategic partnerships, Quantinuum, QuEra, quantum machines, universities, Nvidia is fostering a collaborative ecosystem, making its tools attractive across different hardware modalities. They aren't just building their own walled garden, they're providing the fertile soil, advanced fertilizers, AI, and intelligent farming equipment, DGX QUDA-Q, for the entire quantum landscape. In essence, while others are focused on building the ultimate quantum engine, Nvidia is building the sophisticated AI-powered control systems, the hybrid chassis, and the universal software toolkit needed to turn any powerful engine into a truly effective and usable machine for tackling real-world journeys. This pragmatic, enabling approach might be the smartest bet of all in the unpredictable quantum race. Nvidia's Accelerated Quantum Research Center, NVAQC, isn't just a fancy name. It's a statement of intent and a roadmap for the near future. Starting as early as 2025, the center will become a hive of activity, running intensive quantum simulations specifically designed to test and validate how effectively AI and classical supercomputing can tame the wildness of qubits and improve error correction. This isn't just theoretical work. It's about generating concrete data and refining the AI models. Simultaneously, Nvidia is actively expanding its web of partnerships, bringing more universities, research labs, and private companies into its ecosystem. The goal is clear: accelerate progress through collaboration and ensure their hybrid platform and AI tools become the industry standard for bridging classical and quantum worlds. The real prize: successfully integrating partner QPUs with their DGX Quantum platform, powered by AI stabilization via CUDA-Q. If they can demonstrate significant improvements in the reliability and scale of computations run on existing or near-term quantum hardware, real-world applications could start emerging much sooner than many experts predict. We might see tangible impacts in AI development, cybersecurity protocols, and scientific research within the next few years, rather than waiting a decade or more for hypothetical fault-tolerant machines. Of course, the path won't be easy. Quantum mechanics is notoriously tricky, and developing AI sophisticated enough to truly master quantum error correction in real time is a monumental challenge. Full-scale, universally applicable quantum computing is still likely some way off. However, Nvidia's pragmatic, AI-driven, hybrid approach offers a compelling vision for making quantum power accessible and useful incrementally, starting now. The quantum future is indeed dawning, perhaps faster and in a different shape than many anticipated. Nvidia's journey here offers a fascinating lesson, not just about technology, but about problem-solving in life. Sometimes, the most effective way to tackle a seemingly insurmountable obstacle isn't to attack it head-on with brute force, but to look at your own unique strengths and find a creative, indirect path around or through it. Nvidia isn't trying to out-physicist the physicists building qubits. They're leveraging their mastery of AI and computation to enable those physicists and potentially unlock the whole field. It's a reminder that innovation often comes from connecting disparate fields, from synergy, and from having the wisdom to know what you don't need to build yourself if you can help others build it better. It teaches us that in our own lives, when faced with a huge challenge, maybe the answer isn't always more direct effort in the same direction. Perhaps stepping back, assessing our unique skills and resources, and looking for collaborative or unconventional angles can lead to breakthroughs we never thought possible. What do you think? Does Nvidia's AI hybrid strategy give them a decisive edge in the quantum race? Or will the breakthroughs still come from the companies building the core quantum processors themselves? How soon do you believe we'll see quantum computing making a real difference in our daily lives? Let me know your thoughts in the comments below. I'm genuinely curious to hear your perspective. Thank you so much for joining me on this deep dive into Nvidia's quantum leap. I hope you found it as fascinating as I do. Wishing you good health, boundless curiosity, and the wisdom to find your own unique paths around the challenges you face. If you enjoyed this exploration and want more insights into the cutting edge of technology and its impact on our world, please consider subscribing to the channel. Your support helps us continue bringing these stories to light. Thanks for watching.